let's begin. So let's go over a couple of the variables that we can use for torque. So torque is this Greek letter called tau, and we spell it T-A-U. But essentially, what torque tells us is the, I guess, the quote-unquote force causing the object to rotate. Okay. And the reason why I'm saying it's like a quote unquote force is because torque actually has the variable force in it. But the important idea is that torque is the thing that's causing an object to rotate or to spin around. Okay. And the other variables that are in torque are F for force, and R, which is what we call radial distance. Sometimes we might just call it the radius, but it's how far the force is from the pivot. Okay, so let's go over the word pivot because I'm going to be using the word pivot. Sometimes I'm going to be using the term axis of rotation. But the big idea here is the pivot or the axis of rotation is the point that the object is spinning around. So, for example, if you turn your head side to side, okay, your axis of rotation would be from your neck, right? Or if you were to get your finger and you were to do this with your finger, okay, the axis of rotation would be at the knuckle joint, right? Or if you were to swing your arm around in a circle, the axis of rotation would be at your shoulder joint, right? So with these three variables, we come out with our torque formula, okay? So torque is equal to, by the way, torque is a vector, and vectors are important for denoting like the direction of the way things start to spin. And we've been calling it clockwise and counterclockwise, but in the previous video we went over the right-hand rule for a better way of denoting direction, and that's going to come to fruition in this video here. But torque is equal to F, which is also a vector. And look what we use here for the multiplication symbol, a x and a r with another vector. All right, so let's go over this formula here, and I'm going to show you the other versions that you might see. Now, just so you know that the torque, the F, and the R all have vector symbols above it. I'm just going to shortcut it by not writing them there. So you might see this version, torque is equal to Fr sine theta. And just so you know, this x and this sine theta, they represent the same thing. And the other one is torque is equal to F here, R. And that is the perpendicular symbol. Okay, so I'm going to write that off on the side. So this is for the perpendicular. And all of these things tell us the nature of torque or the requirements of torque. So even though the torque formula only has two variables, F and R, there's actually a total of three requirements for an object to start to spin, which is what we call torque. Okay, so that is force, a radius away from the axis of rotation, and this perpendicular nature. All right, so let's go into one more time the idea of torque. So torque, uh, if an object experiences torque, it will, I guess, cause to spin faster and slower. All right, so it really depends on much like force can cause an object to move faster or to move slower, torque also causes an object to spin faster or spin slower. Now, in a future video, I'm going to go into more in depth of this idea, but there's actually two versions of torque. So we know torque is F cross R, but the other version of torque has this idea of causing it to spin faster and slower. So as you remember, having an object spin faster or slower, this is the idea of acceleration. But because we're in the rotation unit, we're going to use alpha, right? So rotational acceleration. So the other version of torque, which we will focus on a different video, is I alpha. Okay, so if we were to combine these two formulas together, we will get F cross R is equal to I alpha. So if I were to break this down, I would say if you have an object, which is I, your rotational inertia, and that object is spinning faster or slower, alpha, the reason for that is because there is an outside force acting on the object at a distance r away. Right? So the entire formula just communicates with each other. Right? But for this video, let's focus on that formula. All right, so let's go into the cross product. So that x, you just heard me call it the cross product. Now, cross product, you've probably seen it before in your mathematical journey, but in school you were taught many different ways to show that things are being multiplied. So, for example, you could say a times b is equal to c, a times b is equal to c, a times b is equal to c, and a times b is equal to c, right? And there could be other different ones. And you could even argue that the first one and the last one are basically identical. But I'm here to tell you that at least for the first three, right, if you're considering the first one and the last one to be identical, they're all actually describing something different. And we are going to go into this dot later on, but that dot doesn't just mean that you're multiplying. Okay, and that x doesn't mean that you're just multiplying. That x represents what we call a cross product. Okay, and so cross product, if I were to give you a definition, is the idea that the two vectors. Okay, so in this case, we're multiplying two vectors, must be in perpendicular nature. Okay, so that's the idea of cross product. And the way I like to see it is if you draw a big X right there, we have 90-degree angles everywhere. So 90 degrees there, 90 degrees there, right? So there's 90 degrees everywhere. So the idea of cross product is that 90 degrees is the most important thing. The best way to really look at this and to really associate it with torque is by looking at an example. All right, so let's take a look where we have maximum torque. Maximum torque. So in order for us to have maximum torque, I'm going to write down the formula as a whole, Fr sine theta. It's this sine theta that's important. What that means is that we have maximum torque when our angle is at 90 degrees, okay? And the important thing about the two vectors that are at 90 degrees, your force vector and your radial distance vector must be at 90 degrees, okay? So if those two are at 90 degrees, we have maximum torque, right? And so on the other side, sine of 0 degrees, okay, so this is max torque, sine of 0 degrees, sine of 0 just gives us 0. So sine of 0 gives us no torque, right? And here's our example. So you could do this with your arm as an example, right? As you're copying down the notes, imagine this. So let's call this let's call this a, so I'm going to try to draw a person, and this is their arm, right? So their arm is sticking out. So I'm going to draw two arms here. All right, so this arm is sticking out in front of you, and this arm is sticking out like to the side, right? Just so you can see it. And this is the front view, and here this is the top-down view, right? So this is the person's head, this is the person's body, right? And this is the person's arm out in front of you, and this is the person's arm out to the left. And if you want to color code it, I'll color code it here, right? And then here we have this. Okay, so let's do max torque first. All right, so max torque. So when torque is at a max, our vectors are at a 90-degree angle. So if you have out your arm out to the side, and if you're to ask someone, right, or you could even do this yourself, the way that you can rotate your arm is by having someone push on your arm. Okay, and if we are looking at this right from the side view, uh, let's see if I could get a, there we go, let's do good here. This is my axis of rotation right there, right? So that's your shoulder joint, that's your axis of rotation, so your arm is going to pivot around there. And therefore, your radius that the person is going to be exerting a force on, it comes from the axis of rotation all the way out to the far points of your arm. Okay, so this is going to be our R, which is our radius. Okay, so important thing, because vectors require arrowheads. Okay, our radius comes from the axis of rotation out to where the force is being applied. So the person in this sketch here is going to be pushing on, let's say, your hand or your wrist, right? And I'll update my sketch for the other one. So here, this is my axis of rotation, okay? And they are going to push on, let's say, this part of my hand right there. So this is my arm. So the person is going to be pushing on your wrist. Let's do this here. So this is like a weird way to do it, but let's say they're pushing on your wrist into your wrist. And so if you remember from the other video, whenever we say something is into, it's f of x right there. Okay. Now it's kind of hard to see it in a front view, so that's why I have the top-down view. So the person is going to be pushing into your wrist right there. Okay. So if you have your arm out like this and a person is pushing at your wrist, your arm is going to rotate. Right? So it might swing out in this direction. Right? Yeah, well, it will swing out in that direction if you push it like that. It's not gonna, feel good. It might hurt, but that's how it's going to be swinging out. Now let's take a look at the cross product nature. I'm going to use the cross product. Let's do this. Let's make it nice and big. So the important thing is that your R vector and your F vector are at 90 degrees of each other. So here, what this tells us is that whoever is exerting this force, okay, this force is causing max torque, okay, because our force and our radial vector is at 90 degrees. Now, the amount of torque can change if you are pushing at different parts of your arm, and we'll get into that later. But the important thing here is that because your R and your F are at 90 degrees, we have torque, right? Torque exists. Now, what if, I'm going to just ignore this front view. Let's just look at this top view instead. Okay. What if you were to not push at a 90-degree angle? So for example, let's take a look here, right? So our axis of rotation is still right there at the shoulder joint, but the person is now going to instead be pushing into your arm, like so. Okay, so like if you stick out your arm, someone is like pushing against your palm. So we see here that the angle between your R and your F right here, okay, this is 180, and one could argue that's even 0 degrees, right? But the important thing is that your R and your F are parallel. So 180 and 0 degrees, this gives you a parallel nature. So if someone just pushes into your arm like this, your arm's not going to rotate. So for this force, your torque is equal to 0. And that's because your F cross product R gives you 0. By the way, the units for torque is Newton meters, but to look at the sine nature, sine of 0 gives you 0. So even if the person is pushing into your arm at a distance away from the axis of rotation, because it's not at a 90 degrees, we get no torque. No torque. Okay, so you can only have torque if things are at a right angle of each other. All right, so that's the idea of cross product. We see this cross product a lot in nature. We just never thought about it before, where things have to be at a perpendicular nature to each other. All right, let's do a different example. So let's say we have a bar, and that right there, that's my axis of rotation for the bar. Okay, So if we are going to be using our right hand rule here, okay, so in this case we can use like clockwise or counterclockwise, but we can also describe um, the torque using the right hand rule. But for here, if this, let's say we have three different forces, right? So we have one force going up right here. Okay, so if I were to describe, hey, what is this force doing to this bar? You can say, well, that force is going to cause this bar to rotate, and for this case, we'll just say it's rotating in a counterclockwise nature. And if you're at home doing the right hand rule, remember your hand is at the axis of rotation. Okay, your fingers goes into the direction that the object will be curling or rotating, and you can see that the thumb will actually be pointing at your face. And so that way we can say the torque from this force is a O. Okay, or for until we get more practice in, we'll just call it the counterclockwise direction. Okay, so this is the counterclockwise direction. All right. So if we were to take a look at this, just like the previous example here, this is our R, that's our F, and so this force is going to be causing maximum torque. All right. What if we were to do the same thing, right? Same radius R, but the force is pointing in this direction, right? So different scenario, the forces aren't all acting together. We would say, well, in this case, the torque would be, well, the opposite of O would be X, and this force here will cause this bar to rotate in a clockwise fashion. Okay. Now the cool thing about torque is just like forces, we can look at it like net torque. And so net torque, what you're doing is you're seeing what's causing it to rotate in a quote unquote clockwise nature or X's and O's and counterclockwise nature, and you're trying to add them all up. So if our F and our R's are identical for both situations, if you have a person pushing down on this bar and you have a person pushing up on this bar, the net torque would be zero because the two torques would cancel out, right? One causing it to spin clockwise, the other one is causing it to spin counterclockwise, and the total of that would be a net of zero. All right? All right, so what if we were to, let's erase this one here. So in yours, you could add to it, but I don't want to get too messy here. What if you were to have a R that is decreased, okay, but you have the same amount of F from before? Okay? So in this case, because our formula torque is equal to F cross R, because our R went down, but our, in this example here, our F is constant, this force will still cause the object to rotate, but because the R vector has decreased, the amount of torque or the amount of force causing this rotation has decreased, the torque has gotten smaller. So if we were to take a look at the net torque of this scenario here, okay, this torque here is going to cause it to spin clockwise, okay, or in the X direction. And this is causing it to spin the O direction. But if, let's call this R2, because R2 is smaller than R1, but the S are the same, the net torque here would be in the counterclockwise direction, because this torque will be bigger than this torque. All right, and so this object will spin in the counterclockwise direction. All right, now let's do one where we're not looking at 90 degrees. So let's say we have a bar, okay, and we exert a force, let's say, so we'll make this our R, and we're going to be exerting a force right there at that point R. Um, I guess I should draw the vector. There we go. So that's our vector. And the force that we're exerting is off at a angle, like so. That force there. Okay. So the important thing that we're looking at here is the idea of X forces and Y forces. So if I were to break this force down into its X and Y components, okay, remember the direction does matter. So this is F of Y going down, and here we have F of X going in. So if I were to ask you, by the way, we can make this the angle, right? So if I were to ask you, okay, while we take a look at this diagram, which one of these forces is causing a torque? Okay, remember, you're trying to see the vectors that are perpendicular to each other. So if this r vector is along the x-axis, perpendicular to that would be the y-axis, right? And so we can now say that f of x, our torque would be 0 because our theta is parallel, right? So our f and our r are parallel, okay? So the parallel nature causes no torque. So what this means is that your f of y, okay, will be the force that causes the torque. So it is important to say that yes, this force here is going to be causing the torque, but only this y component of the force is causing the torque. The x component is not causing the torque at all. So if we call this our angle, right, this would be f sine theta, right? And we can see here that the torque will be F cross R, and our F here, which we say is F sine theta. Okay, and remember that cross product, we're just looking at the perpendicular nature, and because we are already identifying that Fy is perpendicular to R, we don't have to add another sine theta to that. But look what happens here, F sine theta times R, this gives us our torque formula. Okay, so the reason why I bring that up is a lot of the times when students look at this, right, they see that as f sine theta, and they just automatically go into plug in the variables mode, right? So they say, okay, that's f sine theta, and this is r, and they think, okay, cross product means that there's a sine theta, right? So they want to add another sine theta there, but this is very wrong, right? So this cross product or that sine theta, we are just looking at the perpendicular nature. If you already acknowledge it, and if you are already looking only at the perpendicular stuff, okay, you don't have to worry about that additional sine theta, because that is describing the perpendicular nature of torque. All right, that's it for me. See you next time. Bye-bye.